Okay, we're going to introduce you to this chap here. This chap here is called Blaise Pascal. He was born in 1623 at Clermont in France. His mother died when he was only 3, so he was brought up and he was educated by his father, who was a lawyer and an amateur mathematician. But his dad had some kind of unorthodox thinking about maths and about teaching. He believed that Blaise Pascal, his dad believed that he shouldn't be taught maths until he was 15. It was banned. But Pascal, because it was banned, it became interesting to him. So he would secretly go away and he learned quite a lot of geometry by himself. By the age of 12, he had discovered himself that the angles in a straight line sum to 180 degrees. His father caught him, and once he discovered that his son had a bit of a talent for maths, he decided for him to plough on and with his mathematics education. By the age of 22, Pascal had made some quite interesting observations and inventions. He invented a mechanical calculator to assist his dad in his work with law. But Pascal is probably most famously known for something which is referred to as Pascal's triangle. And Pascal's triangle is so cool. It's got lots of uses within the binomial theorem and binomial expansions and combinatorics. There's also just some beautiful patterns within the binomial or within Pascal's triangle. Okay, so we can make Pascal's triangle really easily. So what we're going to do is we're just going to write a number 1. And what we're going to do below that is the cells directly below that we are going to populate. Okay, so we're going to start, and it starts off as 1, 1, 1. So along the diagonals or on the outside it's always going to be 1s. Okay, so if you want you can fill out some more. Okay, so within Pascal's triangle there's lots of different numbers. Okay, so how we build up these numbers is that to get the value of this box here, we add the 2 boxes above it. Okay, so 1 plus 1 is 2. To get this value here, we will add the 2 boxes above it. 1 plus 2 is 3. Similarly here, the 2 boxes above it, 1 plus 2 is 3. And we can keep going. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 4 and 1 is 5, 10, 10, 5, and then we've got, well, we'll get 6, 15, 20, 15, and 6. Let's do one more. We'll do a couple more rows. So this can obviously go on for an infinite amount of time, but then this next row would be 7, 21, 35, 35, 21, 7, 1. And we'll stop here. Let's go, what's that going to be? 28, what's that? 56, 70, 56, 28, 8 and 1. Okay, so this is known as Pascal's triangle. Okay, so what we do is the number, like any number here, is formed by adding the 2 numbers directly above it. Okay, that's the general rule of Pascal's triangle, where we've got 1s along the outer edge. A few things that are interesting about Pascal's triangle before we get started. There's a few cool wee patterns here. We'll have a look at a few of them. What we can do is we can sum each of these rows. Okay, so like row, 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 row. Let's have a look. So this row here is 1. This row, if we add them together, we get 2. Then we get 4, and then 8, and then we've got 5, 11, 11, 5 is 16. Then over here we've got 20, 30, 32. Can you see a pattern here? Okay, when we sum each row, we get the different powers of 2. Okay, so this is the 6th row, and 2 to the power 6 is 64. 2 to the power 7, 128. 2 to the power 8, 256. Please do check this. It does work. That's one pattern that we do have available to us. I'm just going to rub all this out and we'll show you another one. Okay, so these are the different patterns within Pascal. If we have a look along this diagonal here, we've got all the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, and that would keep going and keep going and keep going. I just rubbed out that 8 there. As well as that, we have got the triangular numbers, 1, 3, 6, 10, 15. For example, from 1 to 3 we go up in 2, 3 to 6 we go up in 3, then up in 4, then up in 5, then up in 6, then up in 7, up to 28. Those numbers can be arranged into a triangle. You can find Fibonacci numbers, you can find prime numbers within here in nice wee patterns. You can build things with fractals from Pascal's triangle as well, which is really cool. One wee thing that we need to be aware of with Pascal's triangle, and what I'm going to do is I'm going to get rid of this grid background. How do I do this? Format background, and I'll go over here. There we go. So, Pascal's triangle can be arranged as the following, and we consider them as rows. It's really important that we consider the first row as row 0, then row 1, row 2, row 3, etc. Okay, so if I wanted to find row 8, I would go here. If I wanted to find row 6, that would be here. So that would be this row of numbers here that would relate to. Okay, so in the last video we worked out, I'm just going to take off these rows. In the last video we were working out binomial coefficients. We worked out 4 choose 2. If we've got 4 objects, we can choose, or how many ways are there to choose 2 of them? And we would use our formula which is given to us in the exam, 4 factorial over 2 factorial times 2 factorial. And I think I remember rightly, we found that was 6. But what's really cool about this is, see this is like the number of objects, and that's the number of like ways, or that's the number of things that we want to choose from said number. So see if we look at this 4, the number of objects, see if we go to the 4th row of Pascal's triangle. And then see if we move to the second item within Pascal's triangle. Okay, so 4 choose 2. So this here would be 4 choose 0. This would be 4 choose 1. Here's 4 choose 2. Okay, so we can get this from Pascal's triangle. If I wanted to work out 7 choose 5, okay, so I would need to go to my 7th row. Okay, so that's going to be this one here because of this 7. Okay, so my 7th row. Okay, and we want to find the 5th element within that row. So this is 0, 1, 2, 3, 4, 5. 7 choose 5 is 21. Can we check that? Well, using our formula, that would be 7 factorial over 5 factorial 2 factorial. 7 times 6 times 5 factorial over 5 factorial 2 factorial. These would simplify, giving us 42 over 2, which is indeed, 42 over 2, which is 21. 42 over 2, which is 21. Okay, so Pascal's triangle actually allows us to work out binomial coefficients. For example, if we wanted to work out, we'll just do a couple more. If we wanted to work out what is 6 choose 3, if I've got 6 objects and I want to choose 3 of them, how many ways are there to do that? Well, if we go to our 6th row and we go to our 3rd element within that row, so this would be 0, 1, 2, 3. 6 choose 3 is 20. Okay, it's really important we always count, like when we're counting across, we go 0, 1, 2. We don't start 1, we start from 0. Let's do one more. 8 choose 8. If I've got 8 objects and I want to arrange or pick 8 of them, well, that should make intuitive sense. There's only one way to do that. It would just be to take those 8, but if we look at that, we go to our 8th row, which is here, and we go along to our 8th element. So 0, 1, 2, 3, 4, 5, 6, 7, 8, which is 1. Or you could have used your formula, which is given to you in the exam, so that will be over 8 factorial, 0 factorial. These would simplify, which would give us 1 over 0 factorial, and know that 0 factorial is 1, which gives us our 1. Okay, so what we can do with Pascal's triangle is we can think about it in a way that, yes, we can calculate problems such as this here, but we could have just used like our formula up here as well. It doesn't matter. We were generally more likely going to use this formula when we're dealing with algebraic terms. When you are asked to calculate 5 choose 3, for example, you've got two options. You could go and do 5 factorial over 3 factorial 2 factorial and just work that out quickly. Or you could just draw your Pascal's triangle really quickly. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So we're doing 5th row, 3rd element. So we're going 5th row, that's element 0, 1, 2, 3. So the answer is 10. Okay, you can do it either way. We'll stop there just now and then we'll have a look at a few examples and just explore this in a wee bit more depth.